The last section in Chapter 4, Section 5, is basically story problems. We're going to model situations either exponentially or with logarithms. So exponential growth. This usually happens where we have population growth, or in science where we have radioactive type things such as decay, bacteria growth or decay. So what happens, since it's continuous, population growth is going to be continuous. We're going to have n at t, my function, the number after a particular time, is equal to n sub naught, my initial and that's going to be e. So it's kind of like my PERT problem. In fact, it's exactly my PERT problem. We're just relating these variables to something other than money. And then it's going to be raised to the RT, where again t is time. So when we have population growth, it's continuous, i.e. that's why we have e, because it's continuous. So when I'm thinking that, I'm also should be thinking the natural log. So let's see, the population in 1973 was 2,500. It's growing at 4% per year. How long will it take the population to reach 7,500? So I know my initial population, and I know my ending population. And I want to know how long, so I'm looking for time. So that's going to be my variable in the problem. A lot of people think E is the variable. Remember, E is not a variable. It is a number equal to 2.71828 that occurs in nature. Then it says raise it to the rate, which is 0.04%. Don't put 4% or 4. It's always got to be put in decimal format. And raise it to the variable t. So hopefully you'll see that this is similar to section 4.4, because now I have a variable in the exponent position. In order to solve for that, I have to start isolating it. So I'm going to divide by the 2,500. 2,500 is 3 equals e to the rate times time. In order to bring that exponent down, I need to use property 3, and I'm going to use it on a natural log instead of a common log. Using it on a natural log brings the exponent down, and I'm left with natural log of e. Natural log, if you recall, is equal to 1. In other words, when I see natural log or common log, I'm asking myself, what is the exponent on the base? In this case, it's e. What is the exponent on e such that I get e? What is the exponent on e such that I get e? That's equal to 1. So that just basically goes away. Divide by 0.04. And now it becomes a calculator problem. Radioactive decay. Well, if it's going to be decay, we have to realize something about the rate or the what's going on there to make it decay. So when you have decay, that factor has to be less than 1. So we had a couple ways of writing a factor less than 1, or factor in this case is less than 1 as well because of that negative. Like population, it's going to have the similar population or the similar formula. We'll just use m in this case. M sub naught, my initial, E. E is 2.71828. And it's continuous, so it must have E. So how do I make then this become decay? How do I make my factor less than 1? Well, that's when I put negative R times T. Time can't be negative. R has to be negative because if I'm decaying, my rate is going down. So we say it's negative. So in a particular case, we're interested in this thing called half-life. So we're going to set h equal to the half-life years. In other words, how many years is it going to take to have half of what I had in the beginning? So not knowing what I start with, we're going to kind of look at this as, okay, let's pretend I start with 1. So in the end, I'm going to have half of that left. Then I have this e, and I'm going to raise it to the negative r h. H is the number of half-life years. Solving this, I already have it isolated because if I divide by 1, it basically goes away. Taking the natural log, I get negative RH natural log of E. And I know that the natural log of e is 1. And since I want to find h or r, I can just solve this. If I want to find r, that means I need to divide by h and negate it. And now I have r is equal to negative 1 over h, natural log of 1/2. And taking a look at that, I think I can simplify it just a little bit further. Rewriting this, let's see, I have negative natural log of 1/2 divided by h. So I just put that fraction together. Now when I look at this, thinking of property 3 again, this negative was really a power. So r now equals the natural log of 1/2 to the negative 1 power over h, which is, see, 1/2 to the negative 1 flips it over, natural log of 2 over h. So there's a quick little simple formula that you can use in a situation if it's asking for the decay rate. So in this case, I know that h is equal to 20. I'm looking for r. So I have a substance. Doesn't matter how much I end up with. If it's half, e to the negative r. And so how do I find r? Well, r then is equal to the natural log of 2 over h, which is 20. Plugging that in your calculator. Now, where did I get this? We just showed where it came from there. So it's going to be negative 0.0346 raised to time, t. Dividing out the 1,000, I get 2 equals e. And if I look at my time here, it says every 20 years. So pretending that I don't know this r that I found earlier, what I'm just trying to show is this formula works out. So if I don't know r, but I know it happened in 20 years, if I take the natural log, r times 20 natural log of e, which is 1, dividing by 20, you can see either you've got choices here. You can, if you choose, go through the process, set it up, and solve to find r, or in general, if you want, you can solve r using this formula. So there's just 2 examples of doing the same problem. This method was very short and simple. I found r without doing much at all because of the formula. If I don't want to use the formula and I just want to strictly plug it in, because I don't want to memorize a formula, I can show here that it works out to be the same. Again, I started with 2,000, sorry, I started with 1,000, ended up with 2,000. E to the, if you look on that, it's going to be RT, and T was 20. And if I just solve this by taking the natural log, I get the same result as I would have if I just memorized that formula. So that's a choice that you can make with what formula you want to use.